All right, let's just jump right in. We've all been there, right? Staring at a coding problem, feeling that pressure, thinking you have to memorize hundreds of different solutions. But what if I told you that's completely the wrong way to think about it? What if the secret was mastering just a handful of core ideas? Well, today we are cracking the code on the patterns that really matter. It's the question, isn't it? The one every single software engineer wrestles with. You know you've got the skills, you can code, but how do you actually perform when the pressure's on and that whiteboard marker is staring back at you? So here's the big reveal. The secret. It's not about the problem. It's about the pattern. I'm serious. It's about the underlying structure. Because once you can see the pattern, you've pretty much already found the key to the solution. This means we're going to completely shift our strategy. Forget about that endless grind of memorizing problems. From now on, it's all about building deep pattern recognition. So let's dive into exactly what those patterns are. So, what are these patterns I keep talking about? Well, think of them like reusable blueprints. They're not just a solution to one single problem. They are a template that you can use to solve whole categories of problems. It's a total game changer. All right, first up, let's get into our first group, linear time scans. The name kind of gives it away, but the big idea here is all about efficiency. We want to solve the problem by looking at each piece of data just once. That's it. No wasted moves. And we're going to start with an absolute classic. You've probably seen it before. Twosome. It's simple, right? You get an array of numbers, you get a target number, and you just have to find two numbers in that list that add up to the target. Sounds easy, but the how is what matters. So the pattern that just blows this problem wide open is the hash map lookup. Here's how it works. As you go through the numbers one by one, you use a hash map to ask a really simple question. Hey, have I already seen the other number I need to make the target? And the magic of the hash map is that it gives you that answer instantly. We're talking near instant O of 1 lookup. Here's a great way to picture it. Imagine you've got a bunch of labeled boxes. For every new number you look at, you first ask, is the partner I need already in one of these boxes? If the answer is yes, boom, you're done. You found it. If not, you just take the current number, put it in its own box, and move on to the next one. Okay, next problem. Valid parentheses. You've seen this one too, I'm sure. You get a string of parentheses, square brackets, curly braces, all mixed up. And the challenge is just to make sure everything is properly matched and ordered. And the super elegant pattern for this? The stack. Just picture a stack of plates. Every time you see an opening bracket, any kind, you push a new plate onto the stack. Then, when you see a closing bracket, you have to look at the very top plate. Does it match? If it's a closing parentheses, is there an opening one on top? If yes, great, you pop it off. But if the wrong plate is on top, or if there are no plates left, you know the string is invalid. And the final check? At the very end, that stack of plates has to be completely empty. And for our last one in this group, let's talk about the sliding window pattern. It's a fantastic one. Just imagine a window that you're sliding over a string. You start on the left and keep expanding the window to the right, one character at a time. The moment you hit a character that's already inside your current window, you stop expanding. Now you start shrinking the window from the left side until that duplicate is gone. All the while, you're keeping track of the biggest window you've ever had. It's a really clever way to check all substrings efficiently. So why do we care so much about this stuff? I mean, what's the big deal? Well, let's go back to twosome. If you just brute force it and check every single possible pair, that's an O of n squared solution. And believe me, that gets really slow, really fast. But when you use the hashing pattern, you get it down to O of n. That's not just a little better, it's a massive leap in efficiency. And that is the power of picking the right pattern. Okay, time for our next set of patterns. Group 2 is what I like to call sorting and pointer magic. These are for those tricky problems where the secret isn't just scanning, but either organizing your data first or using some really clever pointers to navigate through it. First one up, merge intervals. You get a whole collection of time intervals, like meeting times, and your job is to merge all the ones that overlap. The pattern here is this beautiful two-step dance. Step 1, you sort all the intervals by their start time. Step 2, you make one single greedy pass through them to do the merging. And the logic behind this is just so clean. Once you line everything up by when it starts, you can basically just walk down the line. You grab the first interval. Does the next one overlap with it? Yep. Okay, you just merge them into one bigger interval. Does the next one overlap with this new bigger interval? You just keep growing your current block until you hit an interval that's completely separate. Then you start a new block. It's so simple and so effective. All right, next up, how can you tell if a linked list has a cycle, if it loops back on itself? This is another classic problem, and honestly, it has one of the coolest named patterns in all of computer science, Floyd's tortoise and hare. And as the name suggests, it's all about two pointers moving at different speeds. And the analogy is just perfect. Imagine two runners on a track. You've got the tortoise, our slow pointer, just jogging along, moving one step at a time. And you've got the hare, the fast pointer, sprinting, moving 2 steps at a time. Now, if the track is a straight line, the hare just runs off into the distance and finishes. No problem. But if the track is a loop, what's going to happen? Eventually, the sprinter is going to come all the way around and lap the jogger. If those two pointers ever land on the very same spot, you know for a fact you've got a cycle. And that brings us to our final group, the real heavy hitters, logarithmic and heap solutions. These are the patterns you pull out for the truly tough problems, where a simple linear scan just isn't going to cut it. We're talking about incredibly efficient solutions using clever data structures like heaps. So take a problem like search in a rotated sorted array. You have an array that was sorted, but then it got shifted. A normal binary search is broken, right? But a variant of it works perfectly. At every single step, you just have to figure out one thing: which half of the array is still properly sorted. Once you know that, you can ask, could my target number be in that sorted half? If yes, you search there. If no, you know you have to search the other jumbled up half. You're still dividing and conquering, just with an extra twist. Or how about finding the top K most frequent items in a list? This is another great one that uses a two-step pattern. First, you whip out our old friend the hash map to just count up how many times everything appears. Simple enough. Then comes the clever part. You use a min heap, which is a data structure that's really good at one thing, telling you the smallest item it's holding. By keeping the size of this heap limited to K, you can efficiently keep track of the top K biggest numbers you've found so far. Whew, okay. We have covered a ton of ground. So let's bring it all together. Let's distill this down into a powerful, actionable toolkit that you can literally take with you into your very next interview. And this right here, this is your cheat sheet. This is the mental map you want to burn into your brain. The goal is to get to the point where an interviewer says, to sum, and your brain immediately fires back, hashmap O of n. They say merge intervals. You think sort plus greedy, O of n log n. Rotated array, binary search variant, O of log n. It's about creating that instant connection between the problem type, the pattern, and its efficiency. But here's the thing, it's not just about knowing it, it's about how you communicate it. This is so important. When you get a problem, don't just start coding, lead with the pattern. Say something like, this looks like a classic sliding window problem. And then right away, follow up with the time and space complexity. And for bonus points, be proactive. Mention the edge cases you're already thinking about, like nulls or duplicates. Trust me, this shows a level of understanding that impresses interviewers way more than just jumping into the code. So there you have it. We've laid out the map. We've given you the toolkit. The patterns are clear, and the strategy is simple. Recognize, don't memorize. So the only question left for you is, which one of these powerful patterns are you going to master first?